All right, thank you for the introduction. So, as a disclaimer for the audience, this is going to be a crypto talk. There are going to be assumptions. So, if you're all okay with it, I'm going to proceed. Good. So let me describe the settings. So we're now in the settings of two mutually distrustful parties, where an MP relation R is fixed, and the party on the left holds a statement X and a witness W, and the party on the right also knows the statement X, and in addition knows a message M. And now the idea is that the party on the right wants to transmit the message M to the party on the left if the witness W is indeed the correct one, indeed satisfies the relation. So, and this, we model this via a two-round protocol, where the first message is just non-interactive. You can think of it as a non-interactive proof from the first party, and the second message is sort of an encryption. I'll be more formal later, but you can think of it as an encryption that takes as input this small proof and the message, and the party on the left is actually able to recover the message if the statement X and W were indeed to satisfy the relation R. Okay, so this is the problem statement. Let's be slightly more formal. Since it is a two-round protocol, we can actually explicitly define all the algorithms. We have a setup algorithm that sets up a common reference string. A common reference string is given to all parties, and it's assumed to be set up by a trusted party once and for all. In these settings, you'll see that a common reference string is not only useful, but it's actually needed. So we would like to get rid of it, we cannot. And then there's a proof algorithm that takes as input the witness and a statement and returns a proof pi. And you can use this to encrypt and compute the ciphertext C, and the decryption algorithm will succeed if XW is in the relation, as we explained before. Good. So what are the security guarantees that we would like for these primitives? So the only security guarantees, the main security guarantees that we want is that of message indistinguishability. For those of you familiar with witness encryption, this is exactly the same thing. If the statement X is not in the language, then the encryption of two different messages are computationally indistinguishable. And so you should think of this as a CPA security for messages, for statements not in the language. For statement in the language, we do not say anything. In fact, the party on the left should actually be able to recover it, so there is no secrecy needed. And the important part of this talk is that we're going to put constraint on the communication and on the computation of the two parties. In particular, we say that the scheme is laconic if the communication complexity is upper bounded by a fixed polynomial in the security parameter, and that's what the left part means. And the computation of the right party, so of the encryptor, is again depending only on the on a polynomial on the security parameter on the statement X, and in particular does not depend on the size of the witness W, which could be much larger than the statement. That was my sloppy notation on the right means. Good. So for those of you familiar with computationally sound proofs and succinct arguments, you can think of this as very related. In fact, if you ignore the encryption part, the requirements are exactly the same. Good. So, and let me stress one more thing, that we actually do not require the party on the right to know anything about what happened. So you can think of this as the party on the right being completely oblivious of what happened. Okay, so let's look at application to motivate this primitive. So this can be thought as a complexity-preserving maliciousifier, and by complexity-preserving, I mean round complexity-preserving, because I do not add any round to the protocol. Communication preserving, in the sense that the proof pi should be very small. So in terms of communication, it does not add much communication. And computation preserving, in the sense that the part on the right does not have to compute much more, does not have to check the witness relation again. And maliciousifier is a word that I made up, so it doesn't mean anything, but in cryptography we have very often the situation where we have semi-honest protocols to solve tasks, in the sense that all the parties are assumed to behave. And this is of course not the case, but we can compile this into the more realistic malicious settings using zero-knowledge proofs. And you can think of this as a substitute of zero-knowledge proofs, whereas we do not require explicit authentication. So, and slightly more concrete, if you have a message M, you can attach a proof pi such that I can compute the next message M encrypted under this proof pi, and you will receive it only if your first message was well-formed, for some definition of well-formed. Okay? Good. Now, so you may want to ask, why don't you like explicit proof? What's wrong with explicit proof, right? Why don't we just use those? So the problem with explicit proof is that non-interactive succinct arguments are a big open question in cryptography. So we do not know any constructions under standard assumption. And in fact, we have even barriers, that was shown by the work of Gentry Weeks, that they cannot exist from any falsifiable assumption. By falsifiable, you should think of nice assumptions, standard assumption in cryptography. So there are candidate protocols, but they assume essentially that the scheme works. Good. So, and in particular, this framework gives us the first scheme of malicious laconic function evaluation from standard assumption, which I refer you to the paper for this. I'm not going to talk about this today. Okay, so maybe a slightly more concrete application. I want to delegate the computation of a function f, and I'm going to give away a reward for those of you who compute this f of x, and it has to be the correct result, obviously. And maybe it's a bit far-fetched, but there are certain occasions in cryptocurrencies where miners collect together and they want to show that they did some work. It doesn't really matter what work they did, but they receive a reward as long as they made some work. And this essentially gives you the best scheme in terms of all parameters, because the proof is small, it doesn't take too much time to verify, and you can give the reward to the miner. Of course, again, as I said before, you will not be able to explicitly verify the proof unless you add, of course, more rounds of interaction, but we are interested in the 2-round settings. But in this case, it doesn't really matter, because you're not interested in the result, you're just interested in the fact that the miners on the left are doing some work. Good. So I hope I convinced you. So this is the main theorem of the work. So if the computational Diffie-Hellman or LW problem is hard, then there exists a laconic conditional disclosure of secrets for any polynomial size circuit. So that's it. For those of you who are not familiar with the CDH and LW problem, the computational Diffie-Hellman problem is a very old problem. It was essentially one of the first problems where we knew public key cryptography, and the LW stands for learning with errors. It's a very standard problem over lattices. And these two are sort of the bread and butters of public key cryptography. So once you have a primitive from that, which is public key, you can consider yourself happy. Okay, so let me give you an overview of how we construct this beast. The first tool that we are going to consider, so here I list all the tools. So we need PCP, Garbled Circuit, and Laconic Oblivious Transfer. So the order here is in terms of assumption. So the PCP is, of course, an information theoretic object, so we don't need any assumption. Garbled circuits, we need one-way functions. And for Laconic Oblivious Transfer, which I'm going to explain later what it is, we need CDH or LW. And since, of course, CDH and LW imply a one-way function, then we get our result from CDH and LW. Okay, so now I'm going to give a quick overview over these tools, and then I'm going to give an explanation on how we put them together in order to get our result. Okay, so this is my one-slide summary on PCPs. I omitted many of the details, so don't get offended if it's not 100% accurate. So but the idea is the following. So a probabilistically checkable proof allows a prover to encode the witness W into a very large string E, such that the verifier can probe a very few locations of the string E and then verify whether indeed W was a correct witness for X. Good. So, and by correctness, you should always return 1 whenever W is indeed correct. But we have the guarantee that if X is not in the language, then the verifier will not return 1 with probability at least a half. And the important part is that the verifier will only check a constant amount of locations in this encoding. Okay? In cryptography, we're most often interested in negligible soundness, so we are in this work. But this can be always achieved by parallel repetition. So in the end, if you make the calculation, you will get a fixed polynomial amount of probes. So this is going to be important for later, okay? To get negligible soundness in the security parameter. So what is a garbled circuit now? So garbled circuit were introduced by Yao, and it's a very useful tool in cryptography and multi-party computation, and essentially allows one to scramble a circuit in such a way that the evaluator does not learn anything beyond the output of the function, okay? So in particular, let me give you the syntax. The garbling algorithm takes as input a circuit C and produces a scrambled version C prime. And then it produces n pairs of labels where n is the number of input wires. So you can think of as the label, each one corresponding to each input bit. Now, if I'm given a garbled circuit C prime, together with a set of labels corresponding to an input, so I'm taking Li to the power of xi, that means I'm choosing the label corresponding to the ith bit of x. If I'm giving only those labels and the scrambled circuit C prime, then I'm able to learn C of x, so the output of the circuit, but nothing beyond that. This is a very useful concept. Good, so let's fix this in mind. And now let's go to the less standard notion, which is Laconic OT. Laconic oblivious transfer was introduced a few years back by Cho et al. And you can think of this as doing standard oblivious transfer over large data sets. And again, this is also an extremely useful tool. So let's be slightly more concrete. We have a sender and a receiver. A receiver holds a large database and can hash it into a small digest H. So this H is independent of the size of D and can be sent to the sender in just one message. And on the other hand, the sender holds an index I and two messages M0 and M1. And once he receives the hash of the database, he can compute. You can think of this again as a second message of an OT, and send it back to the receiver. Now the receiver, given this message, is going to be able to decode only the message corresponding to the index of his own database. So if the ith position of the database was 0, it will recover M0. If the ith position of the database was 1, it's going to recover M1, okay? And the security is the standard for oblivious transfer, and is the fact that the sender should not learn anything about the database at all, and the receiver doesn't only learn M subscript di and not the message corresponding to the other bit of the database, okay? So this, if you don't put any constraint on the communication, this can be trivially achieved by standard parallel repetition of an OT, but we really want that the communication is independent of the size of D. And again, this is going to be important for later. Okay, so now we have all our three main tools. How do we put them together in order to get our main result? So I'll go slowly over their construction, and if you have questions, please ask me. So the idea is the following. The party on the left holds a witness W and a statement X, and computes a large PCP encoding of that certifies the validity of this relation. Then takes the hash of the Laconic oblivious transfer and hash it down to a very small string. So now this is just the first message of the party on the left. That's it, just the hash of the large PCP encoding. On the other hand, the party on the right, it garbles a circuit, which I'm going to explain in a second, and outputs the scrambled version of this circuit together with all the labels. So this is the important part. What does this circuit do? So the circuit runs the PCP verifier on statement X and goes and queries certain spots of the PCP encoding. So note that at this point, the party on the right does not know the PCP encoding yet, but this is going to be taken as an input. And in particular, we will not need to take as input the full PCP encoding, that would be too large, but just the amount of locations chosen and selected by the PCP verifier over some random coin sample by the party of the right. Okay, so that's essentially what the circuit does. It probes the PCP encoding E on a constant amount of location, polynomial for negligible soundness, and then if indeed everything was fine, it returns M, otherwise it returns both. So then, given the scrambled version of this circuit, the party on the right can just send it, which is C prime. Now, the problem is that it cannot send both labels, L0 and L1, because otherwise the security of the garbled circuit doesn't tell us anything in this case. In fact, all garbled circuits that we know are broken in that case. You shouldn't send both labels. So what we do is instead we condition the sending of each label using a laconic oblivious transfer, and this we can do it because we just send the hash in the first message, right? So for each query of the PCP verifier, we read the query, we let that be the index I of the database, and we condition the transfer on the label on exactly that bit. So what happens, and now we send all this information to the receiver. So what is essentially happening is that now the receiver will be able to recover all the labels corresponding to the locations asked by the PCP verifier and evaluate the circuit locally and able to recover the output if indeed the computation was successful. So now let's analyze quickly the communication complexity of this. The size of the hash is independent of the size of the database. Fantastic, so that's done. And the circuit C is very small because the PCP verifier can be represented by a very small circuit. And again, we have Q messages, one for each query of the PCP verifier, but since we have very little amount of queries, so a polynomial in the number of, in the security parameter, we are good to go. So this is actually independent. You can show that this is independent of the size of the witness. So are we done? No, unfortunately not really. So the problem is that laconic OT schemes are only secure against a semi-honest receiver. And now we're back to the start because we were interested in security against malicious party. So in the original paper, they suggest to transform it into malicious using a non-interactive succinct arguments. But this is extremely not helpful for us because that's exactly what we want to build, an alternative to succinct non-interactive arguments. So we need to design our own scheme. And I don't have time to go. So this is actually the most technically intense part of the paper. And I really don't have time to go through everything. And I'm just going to show an extremely simplified version of the scheme to demystify a bit. And I'm going to make the following simplification. So the first is that we only care about compression of the first message. Then I just care about uniformly random messages for the party on the right. And then I only care about a very weak security notion where a malicious receiver cannot output both messages at the same time. It would be fine, for example, if we could output half of the first and half of the second. You'll see later why. And this is enough to get fully fledged laconic OT via generic transformation, which we show in the paper. And this is our scheme, which is extremely simple. And it gives you a laconic OT from the computational Diffie-Hellman assumption. And you have an element sample. The CRS consists of an element sample from CDHR group. And the hash is just a subset product of those elements. And in order to transfer one of the messages, I just sample a random integer r. And I give all the elements raised to the r except for the ith element. And now you can see that the party on the left will be able to recompute M0 defined by H by computing by H to the R, by computing the correct subset product. If I was 0, that means that the element was not there. And H to the R divided by GI to the R if I was indeed part of the set. So by just taking the same subset product, the party on the left is able to reconstruct the correct message. And you can easily show that this that breaking the security would imply an attack against the computation of the Diffie-Hellman assumption. Okay, so that's all I have to say, and I'm happy to take questions.